All right, most of the GIS work I do is actually with rasters, so I like rasters a lot. Vector's cool. Use them for different things, different applications, so pretty much all GIS folks currently work in both. And I'm going to go ahead and do what we've done in the past and just copy and paste code. However, one of the things I need to do is I need to make sure I'm got everything set up. So notice that I've copied the SpotPy tests folder in here. That way we have the data, including we've got some Mount St. Helens data that's pretty cool. It's before and after the eruption. And then we also have NASA Blue Marble image. It's pretty cool. Also, we've got this temp folder. We haven't talked too much about this, but I am going to go ahead and delete everything out of here. This is from a previous run, and that's so I can watch what happens as the raster tutorials run. Now, also, we've provided you with a new copy of SpotPy because we made some changes to SpotPy raster, fixed some bugs, added some things to make it easier to develop raster Python code. So please place that zip here, and then go ahead and extract that. Now, one of the things that sometimes happens with 7-zip or other decompressions is when you decompress it and you go from here to here, you'll see another folder, right? So if there's another SpotPy folder and then you go into as the Python code, you're going to have to rename this folder, go in and then copy and paste the contents of the SpotPy folder at this level, because what we need to have is our raster tutorial, then SpotPy, then these files. And if you take a look at our Python code, so here's our raster tutorial, and we're saying from SpotPy, import SpotPy base. So the way Python interprets that is it goes and looks for a folder called SpotPy, and if it finds it, then it goes in that folder and it looks for a file called SpotBase. Same thing for all of these other files. So the folder structure is really important because one of the things we're doing here is we're going to override SpotPy that's installed into your copy of Python. In other words, Python will look first to the local directory to see if there are libraries there that fulfill the imports. And if it doesn't find them here, then it will go looking in the Python install folder. Okay, so off and running, there's raster tutorial. And here's the paths to the files we're going to be using. So again, Mount St. Helens is the first couple, and the NASA one we're going to use in a bit. Whoops. Make sure to grab the whole thing. Okay. So these functions, take a look. And feel free to walk through with a breakpoint if you want. It's a good thing to do all the time. Okay, if we go ahead and run this, you'll see that the first thing we do is create a SPA rasters, SPA dataset raster, so very similar to working with vector data. Then we load one of the rasters, the first Mount St. Helens ones. And then there's a whole bunch of functions to get information about the rasters, like the width in pixels and the height in pixels. So that's the number of pixels across and up and down in the raster. The number of bands, most of the rasters we work with are going to be one band, all the DEMs will be, but if you work with remote sense data or satellite images, you're going to have 3 bands, or even Landsats like 7, so you could have different bands. The pixel type, these are based on GDAL, so these are the defines for it, and you'll see that there's 16-bit, 32-bit integer, 32-bit float, 64-bit float. Those are the ones we'll commonly use. Other ones are supported, but these are the ones I tend to use all the time. Coordinate reference system, which we'll talk a little bit about later, and then the actual resolution of the raster, so the dimensions of each pixel. So like DEMs are typically 30-meter DEM is really common, although now with LiDAR we've got 1-meter DEMs that are really cool. And then we've got the bounds, and I'm going to go down here and show you some of this information. So here's our width and height, so small raster, because we're doing demos. 1 band, pixel type 6, not very useful unless you go look up what these are, and then you'll see that I think that's a float 32. You don't really always have to worry about that. And then there's the coordinate reference system, and like I said, we'll talk about this later because this is what's called WKT, or well-known text format. It's really exhaustive in how it describes the spatial reference. A lot of text. Fortunately, we also have an EPSG code, so those are handy and a lot easier to work with than these WKT files. WKT is very closely related to the Esri Proj files. Okay, resolution. Now notice here we've got a tuple coming back. It's like an array. Treat it just like an array, except you can't edit it. That says the pixels are 30 meters by minus 30 meters. So the height is going to go in the negative direction because that's just how spatial data works. And then we have the bounds, x min, y max, x max, and that would be backwards. Darn it. Okay, something else for me to fix on the website. Okay, because that would be wrong. Should go ahead and run that again. And by the time you see this, the website will be fixed. Okay, so then you'll see, here we go, we've got some coordinates. So here's our x min, 500,000, so that's an Easting, working with UTM data. And so there's the westernmost side, easternmost. This is the y min, so that's actually the southernmost pixel in the raster, and then the y max would be the northernmost pixel. So that gives us the bounds of our raster. And then there's some other statistics. This work is all based off of GDAL and the other open source libraries. So this is just another set of information that it has for us. I don't really use that much. And then one of the cool things about doing open source work is we can go right into the raster bands. Here's the actual data for the raster. So we can get the band and then just print it out. It's just a two-dimensional array. Now because we can have multiple bands, well, wait, sorry. Oh yeah, it's just two-dimensional array. So there's one row of raster data. Of course, it's longer. That's what these dot dot dots mean. And then there's an array that contains these arrays. Each of the inner arrays is one row of data. So pretty cool that we can just dive right into the data. It's one of the reasons I like working with open source because it tends to be much easier to dive right into the data. All right, so let's do some interesting things. Here's how we clip a raster. Now it's a little bit hard to keep track of where we are, so I'm going to put in some hash marks, of course. And all I've done is specified an array that has our bounds in it. This is really common, used in both open source and code that I work with. So we've got a new x min, x max. Now when you open this up, it's kind of hard to tell, but you can see that we've just got the volcano. If I go ahead and show the original data set, did we load it? Yeah, there it is. Raster file 1, raster file 1. Similar to the vector commands, you can either pass in a data set or a file, and SpotPy will figure out which one. So you can see this is the whole DEM. Okay, so it's not only Mount St. Helens before the eruption, but also the area around it. And when we keep going, you'll see that here we've cropped out just the volcano itself, pre-eruption. And I'm going to go ahead and comment those out so we don't have to see them every time, and move on to the next one. So resampling changes the resolution of the image, resamples it. This is really important when we're working with large data sets, especially when you just get started. You don't want to work with huge data sets. So what we can do is, it's called resample, and then you send it a factor to resample it, and then you'll see that I print out the width. Now the reason I print out the width is because when you resample a raster, it's really hard to tell that it's any different than the original, right? It just doesn't look that different. But what you can see is we resampled, the width was 327, and then we do this resample at 0.5, and that's reduced the resolution by a factor of 2 to 164, or it's cut the number of pixels in half. So lower resolution data, which is normally what we want to do. You want to take high resolution, you want to resample it to low resolution so it's faster to work with. Then when you get your algorithms, your code working, then you want to run it on the whole thing. Okay, then down here we actually bump up the resolution, increase the resolution. Again, we don't do this as often. So now the width of the new one is 490. Cool. Okay, so these are very commonly used to work with raster data. And it looks like that is all that's in that tutorial. A short one. And then reprojecting. Reprojecting rasters is a little bit different than vector data. I'm on this page going to copy and paste this code into my file, and you'll see that what this code does is it goes ahead and gets a blue marble image. This is a set of data from NASA. It's a very cool set of images. And you can see here that I've reprojected that into UTM and displayed it. The function to do that is called transform raster. And you'll see it's a little different because it does require a file name for the destination file. So you pass it a data set or a file name. You have to provide it a file name. And the reason for that is because rasters can be quite large, and GDAL writes them out to disk as it's doing the reprojection. You can see that I've just provided the EPSG number for UTM Zone 10 North, WGS84, and that's it. That's all that's required. Very easy to reproject. And let's go back. Now, that's for all the spatial references that are covered by EPSG codes. If you want to do something else, which might happen, you can do everything that's supported by Proj, which is far more than I've ever needed. Like here we're doing an Albers equal area, longitude 0 for the origin, longitude of origin, and then a latitude for the start of the northernmost point of the study area, and then the southernmost point of the study area, and the datum's WGS84. So this little parameter block here is a Python dictionary is what it's called. You can see from the braces. And then each of these are keys with values after them to tell Proj how to do the spatial referencing or the projecting. So here we're again calling transform raster, and then instead of doing the EPSG code, we're just specifying those parameters. And I'm going to save that to a file and then show it. And then just to show that it works both ways, I'm also going to project that back to WGS84 geographic. Now, Albers takes a while, and if you have a big raster, this function can take quite a while to do the transformation or the projection. But there it is. So Albers equal area, the whole world, kind of cool. And if I close that, it's going to continue on and then transform it back to geographic. And you'll see it's back to geographic, but with a little bit of distortion, because that's going to happen every time you do projecting. And a lot of other transforms, you're going to get some errors in there. So projecting back isn't perfect, but it does work.